This is the 10th video in a series devoted to introductory proofwriting. And today we're going to talk about mathematical results, kind of the terminology behind mathematical results. And then we're going to start learning how to prove conditional statements. Okay, so there are lots of different names for mathematical results. And in fact, there's a bit of a hierarchy to these results that it's useful to know a little bit about. Although just be aware that this isn't really a strict hierarchy. So a lemma can be thought of as a very, very small result, but not really a small result that stands on its own, but it's generally thought of as a building block for a theorem, or a building block for a step in a proof of a theorem. And then often theorems are such big results that you'd like to look at some very special cases of a theorem, or look at something that follows very quickly from a theorem, and that's called a corollary. And then furthermore, if you have a result that's not quite as big as a theorem, whatever that means, you might call it a proposition. Now, kind of on the level of proposition, you have these other names of results, claim or observation. Often a claim is something inside of a proof, but it doesn't have to be. In fact, when I was in grad school, I had a professor use the name meditation for a result in class once. I thought that was pretty funny. And now a result that we don't know if it's true or false is called a conjecture. So all of these are known to be true. So there are proofs of every theorem, proposition, lemma, corollary, and so on and so forth. So if we, as the mathematical community, are calling a result a theorem, proposition, lemma, so on and so forth, then it has a proof and it is known to be true. So something that does not have a proof is called a conjecture. But often some of this stuff has historical naming to it. Like, for example, Zorn's lemma is equivalent to the axiom of choice. But that kind of makes it a fairly large result, but it's called Zorn's lemma. And I'm sure there are other examples of things like that that have historical names, even though the size of the result maybe doesn't match the naming convention. So here are some examples of results. So the first one says, if the sum as n goes from 1 to infinity of a sub n converges, then the limit as n goes to infinity of a sub n is equal to 0. So if a series converges, then its terms go to 0. So this is an example of a conditional statement. So it's of the form P implies Q. So the statement P would be the series converges, and that implies the statement Q, which is that this limit is equal to 0. Let's look at another example. So you probably learned this other example in a linear algebra class. It says an n by n matrix A is invertible if and only if its null space contains only the 0 vector. So this is an example of a biconditional statement. We would read this as P if and only if Q. And then there are also non-conditional statements, such as the harmonic series, which is the sum as n goes from 1 to infinity of 1 over n diverges. Notice this isn't of the form if P then Q. That's a non-conditional statement. So we'll learn how to prove conditional, biconditional, and non-conditional statements in this course. But that being said, we will start with conditional statements. But before we can get off the ground, we really need an explosion of very basic definitions to work off of. And so let's get those on the board. Okay, now we've got a boatload of basic definitions which we'll use in order to start our very basic proofs. And I don't think it's reasonable to memorize all these definitions right now. You'd probably just like to keep them written down somewhere near you or kind of at the ready to use whenever you see them within some sort of result that we're trying to prove. Okay, so let's maybe just go through them one by Okay, so let's go through them one at a time. So an integer n is even if n is equal to 2k for some k which is an integer. So it's a multiple of 2. An integer n is odd if it's of the form 2k plus 1 for some k in the integers. The parity of an integer is its evenness or its oddness. So we would say that the parity of 5 is odd. Or maybe we would say the parity of 5 is 1, but that's kind of getting ahead of ourselves. So m and n have the same parity if they're both even or they are both odd. So 3 and 5 have the same parity. M and n have opposite parity if one is even and the other is odd. For example, 19 and 100 have opposite parity. Next, if we've got two integers a and b, we say that a divides b, and we write, well, I'm going to read this a divides b, but it's a and a vertical line b, if there is a d such that b is equal to a times d. So there's some dual way of saying this. So if a divides b, then b is a multiple of a. So sometimes we'll be saying b is a multiple of a, and sometimes we'll be saying a divides b, but those have the same meaning. Next, we say a natural number p, which is not equal to 1, is prime if its only divisors are 1 and p. So like, for example, 17 is prime. Next, we say a natural number which is not equal to 1 is composite if it's not prime. And in fact, all composites can be written of the form a times b, where a and b are strictly between 1 and n, where n is that composite number. You might notice that neither of these definitions say anything about, well, what happens if we're talking about the number 1 itself? That's because it plays a special role. 1 is called the unit of the natural numbers. So I didn't write that down here, but I'll just say it out loud. 1 is the unit of the natural numbers. So in general, in larger number systems, if you will, there are units, composites, and primes, or sometimes those primes become irreducibles. So those are your three types of numbers in larger number systems. So it's just kind of a bummer that within the natural numbers there's only one unit, so it seems to be playing this unique role, whereas in other number systems more objects are units. Okay, so moving on to the next two definitions. So given two integers a and b, we say that d is the greatest common divisor of a and b, and we write it as d equals GCD AB. If d divides a and d divides b, so it's a common divisor, and then it's got to be the biggest common divisor, but we encode that using divisibility. So if we have another common divisor c, so c divides a and c divides b, then c divides d. So that ensures that d is the largest such common divisor. Then what about the least common multiple? That's like dual to the notion of the greatest common divisor. So we'll say that L is the least common multiple, and we'll write L equals LCM AB. If A divides L, B divides L. And if A divides M and B divides M, then L divides M. So this condition over here ensures that L is both a multiple of A and B. But then this condition here ensures that if we have another multiple, it is larger. Okay, so like I said, we probably don't need to memorize these just yet, although after doing lots of examples, you'll hopefully internalize all of these definitions. But we'd like to be able to unpack and repack these definitions as needed for our basic proof. Now we're ready to start writing down some very, very basic proofs. We're going to start with what's called the method of direct proof, which is used to prove conditional statements like if P then Q, or P implies Q symbolically. And so in fact, I think there's this nice outline that we can use for inspiration of how to write this proof in the first place. My suggestion would be to essentially follow this outline for your first several proofs, and then you can start maybe adding your own creative flavor to them. Okay. So let's say we've got this proposition, if P then Q. And P and Q can both be really, really complicated mathematical statements. But our goal is to show that one implies the other. So how does the proof go? So based off the truth table of the implication statement, P implies Q, which I'll let you review if you need to, what we'd like to do is suppose that P is a true statement and show that that leads to the truth of Q as a statement. So we'll just say right here, suppose P, and what the undertext there is we're supposing P is true. And then we end with thus Q, and the undertext there is thus Q is true. And in the middle, you know, it's going to vary from proof to proof, but the general strategy will be to unpack the statement P via definitions, Probably since we're just starting it out, it'll be one of those definitions that we just saw on the board. So what I mean by unpack with definitions, I mean rewrite what it means for P to be whatever we're saying it is into like some equations or something. And then we'll make the appropriate calculations and logical arguments to get to a point where we can repack into Q via definitions. Okay, so this is all well and good, but I think it's better just to look at some examples. Actually, it's probably best to look at a ton of examples and then try examples on your own and then revisit this outline so that you have a more holistic view on it. So that, in fact, would be my suggestion. Okay, so let's do this first example. We'll prove this simple proposition. If n is odd, then n squared is odd. So just going through some typical examples of odd numbers, this seems very true. So 5 is an odd number. 5 times 5 is 25, which is an odd number. 11 is an odd number. 11 squared is 121, which is also an odd number. So it seems like we're good to go here. But let's write this proof down. So let's suppose that n is an integer and n is odd. Okay, so I filled in a little bit of the detail there. I said that it was an integer. That's kind of subtext of this statement, but that's okay. Now we'd like to unpack what it means to be odd via definitions. Well, we had a definition of that on the previous board. So that means, we have a k, which is an integer, such that n is equal to 2 times k plus 1. That was our definition of oddness. But now we've written oddness as some sort of equation. And since we need to square n, that gives us something like meaty to do some calculations with. Okay, so now let's go from there. Now we've kind of unpacked the left-hand side, the P statement totally, and we can see what the right-hand side is saying. It's motivating us to square this thing. So let's do that. So I'll write it like this. So let's notice that n squared is equal to 2 times k plus 1 squared. That's because n is 2k plus 1. Then we can multiply this out to 4k squared plus 4k plus 1. But then notice that we've got something times 4 plus 1. But 4 is an even number itself, so we can factor 2 out of each of those. So we can factor a 2 out of these first two, and that leaves us with 2k squared plus 2k plus 1. Okay, so let's see what we have. We have n squared is equal to 2 times something plus 1. So if we wanted to be super clear here, we could do that. And maybe we would use some language like observe that n squared equals 2 times a plus 1, where a is equal to 2k plus 2. Sorry, that should be 2k squared plus 2. And then we can repack this expression for n squared into the oddness of n squared. So we would end with thus, n squared is odd. Because recall, by our definition, if a number can be written as 2 times something plus 1, it is odd. Okay, let's do another. For our next example, we'll prove that if n is a natural number, then the expression 1 plus negative 1 to the n times 2n minus 1 is a multiple of 4. Okay, well, this is not quite the same sort of conditional statement because there's nothing really to unpack of our hypothesis here. So our hypothesis is just that n is a natural number. Like I said, there's nothing to unpack there. But there is a little bit of motivation for how to proceed by the shape of this object that we have in the conclusion. Notice we have minus 1 to the n power. And let's recall that minus 1 to an even power is positive, whereas minus 1 to an odd power is negative. So this object seems to behave differently depending on the parity of n, the evenness or oddness of n. So that motivates us to look at those two cases separately. So let's do that. So we're still going to start the same way. So we'll suppose that our hypothesis is satisfied. So we'll suppose that n is a natural number. And then we'll notice that this tells us that n is even or odd. So thus, n is even or n is odd, because every natural number, in fact, every integer is either even or odd. And now we're going to split this into two cases. It's pretty typical to explicitly write down that we're splitting into cases like this. So case one will be maybe n is even. Whereas case two, I'll put it down here, I think that'll give me enough room, will be the case when n is odd. Now we want to decompose what it means to be even or odd. Okay, so let's do it. So in this case, we have n equals 2k for some natural number k. And we know it's a natural number because we're starting within the natural numbers. So now let's plug that version of n into our expression, this being our expression. So maybe we'll use this language again. Notice that 1 plus -1 to the n times 2n minus 1 now has the form 1 plus -1 to the 2k times 4k minus 1. It's 4k minus 1 because we have a 2 times n right here. Okay, but now let's notice that -1 to the 2k is definitely +1, given that 2k is even. So this simplifies down to 1 plus 4k minus 1, which is equal to 4 times k, which is a multiple of 4. So we would maybe put a comma here and then note at the end a multiple of 4. So at least in this case, when n is even, we have achieved that our expression is a multiple of 4. Now let's do it in the case that n is odd. Okay, but notice that since we don't have all integers here, we'll need to use a slightly different expression for n being odd, and that will be of the form 2k minus 1. That's because if we use 2k plus 1, we can't achieve the odd natural number 1. I'll let you think about that, but in the end, it's not that huge of a deal. Okay, so the case when n is odd. So in this case, we have n is equal to 2k minus 1 for, like I said, some natural number k. And now we'll essentially do the same thing, but just with this value of n instead of the 2k value of n. So I'll use the same language. Notice that 1 plus -1 to the n times 2n minus 1 in this case is equal to 1 plus -1 to the 2k minus 1 times, so this is going to end up being 4k minus 2 minus 1. Right, so it's 4k minus 2 because if we multiply this thing by 2, we get 4k minus 2. Okay, but now let's do our calculation. This ends up being 1 minus 4k plus 2 plus 1. That's because this object, minus 1 to the 2k minus 1, is a -1 given that we have an odd exponent. But now putting this all together, we have 4 minus 4k, which is the same thing as 4 times 1 minus k. But that's also a multiple of 4. So either way we look at it, if n is even, we get a multiple of 4, and if n is odd, we also get a multiple of 4. So that's the end of this proof. Let's do another. For our next result, we'll prove that if m and n, which are integers, have the same parity, then their sum is always even. So this is going to, again, break down into two cases. So, and those cases are based off both being even or both being odd. But let's write that out. So let's suppose that m and n are both integers with the same parity. So we're assuming that the hypothesis is true, and just like we've been doing this whole time, we want to prove that that will imply the conclusion is true. Okay, so m and n are both even or both odd. That's exactly what it means for them to have the same parity. Now we'll split into cases. So case number 1 again, let's say m and n are both odd. So let's work through this. So what does this tell us? This tells us we can write m as 2a plus 1 and n as 2b plus 1, where a and b are integers. That's the definition of them each being odd. And now we'll notice that their sum will end up being even. So let's notice that m plus n is in this case 2a plus 1 plus 2b plus 1. But now we can put this all together and get 2 times a plus 2 times b plus 2. Factor a 2 out, we get 2 times a plus b plus 1, which is even. Great. So we showed that if we started with two odd numbers and we took their sum, we got an even number. And actually, I'll leave case 2 as a little bit of a homework exercise, but it should follow fairly similarly. Okay, so now we're going to look at something called a contrapositive. For our next set of examples, we're going to look at something known as a contrapositive proof. So let's recall that a conditional statement is logically equivalent to its contrapositive. So that means if we can prove that the contrapositive of a statement is true, that means that the original statement is also true. Well, let's recall what the contrapositive is in the first place. So if we have a conditional statement, P implies Q, its contrapositive is the statement not Q implies not P. And like I said, those are logically equivalent, which you can show with a truth table if you'd like to, but likely you did on your homework already. So what's the outline for a contrapositive proof? Well, it's just essentially a direct proof of the contrapositive of the statement. So there's nothing really there. Let's say we've got the statement, if P then Q, and so you would suppose not Q, and then do calculations and whatever, just like we had talked about before, and end up with thus not P. And so this proof has shown not Q implies not P, which, like we've been saying, is logically equivalent to the original statement. But I think maybe the really important question here is, how do you know whether to use a contrapositive proof or use just direct proof? And while there's no like tried and true method, the way that I think about it is the simplicity of the statements. So generally, it's easier to prove a statement if it starts with something simple in the hypothesis and you have something a little bit more complicated in the conclusion. So in other words, you're taking a simple statement implies a complicated statement. So if P is a simple statement and Q is a more complicated statement, you probably want to use the method of direct proof. Whereas if P is a complicated statement and Q is a simple statement, then you probably want to use the method of contrapositive proof. And that's because it essentially like changes the direction of this arrow. Of course, there's some negation there, but it takes you from simple to complicated when you weren't originally set up to do it that way. Okay, so we're going to do a couple of examples starting with this one. So let's suppose that we have real numbers x and y, and now we want to show that y cubed plus x squared y is less than or equal to x cubed plus xy squared implies that y is less than or equal to x. So this is a classic example of this thing that I was telling you down here. We've got a fairly complicated hypothesis and a very simple conclusion, which is kind of like backwards of what you would like. So we'll look at the contrapositive. Maybe let's write it out for this first one. We generally won't write it out, at least in the final proof. You might want to write it out on your scratch paper. So what does the contrapositive say? It says if y is not less than or equal to x, in other words, y is strictly bigger than x, then y cubed plus x squared y is strictly bigger than x cubed plus xy squared. So those non-strict inequalities changed directions and turned into strict inequalities. So this is the statement that we will prove. And often, at least when we're starting out, we'll indicate that we're proving something by contrapositive at the beginning of the proof. I'll just put it in parentheses. So contrapositive. Great. And that's mostly for the reader, but generally in higher level math classes, you wouldn't write that you were doing it by contrapositive. Okay, so now let's suppose that we have y bigger than x. So that's like supposing not q in this case. And now we want to work towards this inequality right here. But notice if y is bigger than x, we can immediately see that y minus x is bigger than 0. And x and y are both not 0. It's clear that they're both not 0 or not both 0 because if they were both 0, if we took their difference, we would get something that's 0. Okay, but if they're both not 0, then if you square them and add them together, you get a strictly positive number. So let's write that down. So thus, x squared plus y squared is a strictly positive number. Why do we want to look at x squared plus y squared? Well, the stuff over here on the right-hand side seems like it looks like the stuff over here where we've multiplied by x squared plus y squared. Okay, so that motivates the following calculation. So I'll just write, notice that we have y minus x times x squared plus y squared is bigger than 0 times x squared plus y squared. So the inequality is inherited from this inequality right here, y minus x is bigger than 0, and the fact that we're multiplying by something positive. So that does not change the direction of the inequality. Okay, so after expanding out the left-hand side, hopefully we have something nice. So let's see what we have after expanding out the left-hand side. We'll have x squared y plus y cubed minus x cubed minus xy squared. And then over there on the right-hand side, we'll have 0 because 0 times anything is 0. But look at what we have. Everything which is a positive term is this stuff over here, and everything that's attached to a negative is this stuff on the right-hand side of the inequality. So when we move when we move everything with a minus sign over, we get exactly our inequality, our not p statement. So we can just finish this off by saying, thus x squared y plus y cubed is strictly bigger than x cubed minus xy squared. Sorry, that should be plus xy squared. But that's what we wanted to show. So that finishes the proof of this statement by contrapositive. Let's do another. So for our next result, we'll start off with two integers m and n, and we'll prove that if 3 does not divide m times n, then 3 does not divide m and 3 does not divide n. And we're going to use the contrapositive again here. But the interesting thing about this is that our conclusion, which maybe I'll put in these orange brackets, this conclusion is an and statement. So that's pretty cool because we have to negate an and statement, which will turn into an or statement. Okay, so now let's suppose not Q, which in this case would be not this and statement. So suppose that 3 divides m or 3 divides n. So that's by one of De Morgan's laws, right? And so saying 3 does not divide m is the same thing as 3 divides m. Same thing for 3 and n. And then like I said, and turns to an or. Okay, but now let's notice that in our entire setup right here, m and n are playing in symmetric roles. But since they're playing in symmetric roles, it doesn't matter whether or not we decide that 3 divides m or 3 divides n. But there's a careful way of writing that down, and that's using the phrase without loss of generality. So without loss of generality, we will assume that 3 divides m, and then that's the same thing as saying that m is equal to 3 times k, where k is some integer. That's what it means to be divisible by 3. So you have to be careful with this phrase without loss of generality, or also the tool which we'll learn later, similarly, because they're not always applicable. You have to be really sure that it's the same calculation if you choose m to be a multiple of 3 or n to be a multiple of 3, or that m and n are playing symmetric roles in your setup. So here we're okay. Okay, so now we have everything that we need to work towards the conclusion of the contrapositive statement, which should be the negation of 3 does not divide mn. So that means we're trying to get to 3 divides mn. In other words, mn is a multiple of 3. Okay, so let's look at mn. So maybe we'll just say observe that, so m times n is now equal to 3 times k times n by replacing m with 3k by our setup. But that's equal to 3 times nk. But since mn is a multiple of 3, we can say that 3 divides mn as needed. And that finishes this proof off. Okay, we're going to look at one more basic definition, which we weren't quite ready to put in that big list at the beginning. And then we'll do a proof with that definition, and then we'll end with some warm-up exercises. So this next example plays a very important role in elementary number theory, and it's another useful thing to have under our belts for doing basic proofs. So given integers a and b, and then a natural number n, we'll say that a and b are congruent modulo n if n divides a minus b. So in other words, a minus b is a multiple of n. Later we'll see that that's equivalent to a and b having the same remainder when dividing by n. That'll be a nice homework exercise. And then in this case, we'll write, well, I'm going to read this as a is congruent to b mod n, but this is the notation here. We have this triple equal sign here, and then in parentheses, mod n. So let's look at some quick examples. So 12 is congruent to 2 mod 5. That's because 5 divides 12 minus 2. Of course, 12 minus 2 is equal to 10. 34 is congruent to negative 2 mod 9. It's really important to consider negative numbers mod n as well. Sometimes that'll be super helpful. And that's because 9 divides 34 minus negative 2. 34 minus negative 2 is, of course, 34 plus 2, which is 36. That's a multiple of 9. Then 57 is congruent to 0 mod 3. So notice 3 times 10 is equal to 30. 3 times 9 is equal to 27. That means 3 times 19 is equal to 57. Notice 57 would also be 0 mod 19. Finally, if we have two numbers that are incongruent mod n, we say, well, like I said, we say they are incongruent or not congruent mod n. And we would write it like this. So with this slash through the triple equal sign. So we would read that as 13 is not congruent to 5 mod 3. Okay, so here's a nice first example of calculations that you might do with congruence mod n. So let's suppose that a and b are congruent mod n. Then we want to show that a squared and b squared are congruent mod n. Okay, so this is a conditional, a P implies Q statement. Let's suppose that the hypothesis is true. So let's suppose that A is congruent to B modulo n. And now we're going to unpack this all the way to an equation. So this will take a couple of steps. So thus, n divides A minus B. And what I really mean by that is that A minus B is equal to n times k for some integer k. So let's see, we did a stepwise unpacking of this definition. So we started with A is congruent to B mod n. We moved that to n divides A minus B. But if n divides A minus B is a multiple of n, so we can write A minus B as n times something. Okay, great. But now we'd like to get at A squared and B squared. But since these are on opposite sides of the congruence and these are on the same side of the equation, perhaps we'd like to move some things around. So maybe we would rewrite this as A equals B plus nk. But then how would we write that in language? Well, maybe we'll just say that we will write A equals B plus n times K, and then we'll say observe or notice or something that this calculation will finish us off. So we've got A squared is the same thing as B plus n times K squared, but multiplying that out gives us B squared plus 2 times B times n times K plus n squared K squared. But the important thing is that all of this stuff here is a multiple of n. So that means we can write the following. A squared minus B squared is equal to n times, it'll be 2 times B times K, and then plus n times K squared. But that's the same thing as saying n divides A squared minus B squared. We have A squared minus B squared is a multiple of n. But n dividing A squared minus B squared is the same thing as saying A squared is congruent to B squared modulo n, which is exactly where we wanted to end up. Okay, so that's good. Now I'll leave you with some warm-up exercises. So I've got 4 warm-up exercises for you. So the first is to read section 5.3 of the Book of Proof. So the class that I'm teaching based around this material is using the Book of Proof. I think section 5.3 is a really nice take on the style of mathematical writing. Then for number 2, let's show that if we've got integers m and n that are the same parity, then 5m minus 1 and n plus 10 do not have the same parity. Next, let's show that if we have integers x and y, if x squared plus 2 times y minus 1 is even, then x is even and y is odd. And finally, show that if we've got integers a and b, then a plus b cubed is congruent to a cubed plus b cubed mod 3. Now, I'll just say that we have the methods of direct proof and contrapositive proof to work with for all of these examples. And that's a good place to stop.